Okay, so time to start. From this week, we convert to e-learning mode. So but since still people show up, I'm very happy. So I'll continue as usual. For tutorials, it is still going on. So NUS only canceled the classes with more than 50 students. So our tutorial size is less than 50. So the tutorial is continuing. Okay. All right. So we are in the topic of counting. So last time we talked about binomial theorems, which is the expansion of this sum, a plus b to the power of n. And then we stop at this slide. So there's a name for the binomial coefficients. So this triangle has a name called Pascal triangle. So it formed, you can think of it as formed this way. You have two rows of ones on the border. Now, for any cell in the middle, it has two neighbors. One is upper left, one is upper right. And then the number you see in this cell, for example, is the sum of his two neighbors, upstairs neighbors. So for example, the 2 is 1 plus 1. Now randomly pick one, right? This 35 is, you see, it's the sum of the two neighbors upstairs, 15 plus 20. Okay. So, so this is observation. So you can think of the Pascal triangle was formed this way. Okay. Now, yes. So observation, we already made it. Now we know the binomial coefficient. Okay. So last time we showed that the binomial coefficients actually is this n choose k. Okay. So if you turn this observation into a mathematical formula, it says if you look at this cell, suppose the cell is on the n plus 1th row, and from left to right is at position k, then it is a sum of these two upstairs neighbors. Now if you check the address of the neighbors, so they are on the nth row, but their address are one from the k minus 1 cell, one from the kth cell. So the observation, if we write them in mathematical terms, is this equality. Okay. Now, of course, mathematicians want to prove everything, right? Just by looking at it is not enough. So we have our disease. We have to prove. Okay. So I'll give you two proofs to convince you this is the case. Each of the proof has their own merit. Okay. So the first proof is called the counting argument. You may have heard of this several times. Counting argument to show an equality basically is the following method. So you count the family of objects. You count them in two ways. Counting in one way give you left-hand side. Counting in the other way give you right-hand side. And because we are counting of the same family, just by two different ways, so the number must be equal. So this is when people mention counting argument, it's more or less like this argument. Now we are doing, okay, so let's prove this equality by the so-called counting argument. Okay, so now I want to count the left-hand side in a certain way, right? So this is n plus 1 choose k. Now we have seen the example, n plus 1 choose k can be viewed like this is the number of k-person committee formed from n plus 1 persons, right? From this collection of people, you form a k-person committee, right? So this left-hand side is n plus 1 choose k is exactly the number of k-person committee formed from n plus 1 person. So this is one way of counting the thing, right? Now I want to count the number of ways to form k-person committee in a different way. Hopefully give us the right hand side. Okay, so now let's imagine you, okay, each one of you, you are one of the n+1 candidates. Okay, so now you count the number of this k-person committee, the possibilities, in two ways. So you count in two cases. You count those committees which includes you, right? So then the number, total number is n choose k minus 1. Why? Because you are in the committee, so you take one of the k positions. So this becomes k minus 1. But on the other hand, you also exclude yourself from n+1, right? So you become n person, right? So it's like from n person you choose k minus 1 people. So that's the case where you are inside, you are in the committee. Now there's also a case you are not in the committee, right? Counting those committees which excluded you. So the total number will be, so you are not among the choices, so it's among, so there's n person. Now in the n person you have to choose k of them, so you choose this is cnk. So therefore the total number of ways is case 1 plus case 2. So it's this number. But we are counting the same objects, right? They are the k-person committee formed from n+1 persons. We are counting the same thing, just using different method. So therefore, the equality holds. So this is one argument. Now the other argument is, okay, I don't like to think too much. I just want to compute. Okay, so we know that we can write n choose k as an expression using factorials. So the factorials for beginners looks very difficult. So, but maybe by showing this, we get more familiar, we get more practice of how to handle factorials. Okay, so let's try to just manipulating the formulas. Hopefully we can prove the equality. Okay, so let's try. So by definition, sort of definition, we know that n choose k is this this expression. So it's n factorial divided by n minus 1 factorial n minus k factorial times k factorial. Right? So we have shown this. Now the second term, n choose k minus 1, if you plug in the numbers, is n factorial divided by, okay, so this is n minus k minus 1, n minus bracket k minus 1. It becomes n minus k plus 1, right, the first term. The second term is k minus 1 factorial. Okay, so we have the sum. Okay, now we want to take out common factors. So the numerator is easy. It's just n factorial take out. Now the denominator, it needs practice, right? So let's see. So what is n minus k factorial? So this is n minus okay, so I want to do things slowly. So let's see. Can I write it here? Good. So I want to take out the common factors from the denominator. Okay, so maybe the k factorial is easy. So let's see. So this is the middle steps. So observe that k factorial is 1 times 2 times 3 dot 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 times k minus 1 times k. Right? This is the menial factorial. Now, how about k minus 1 factorial? So this is the same thing. This is 1 times 2 times 3 dot 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 but we stop at k minus 1. Okay, so therefore the common factor are the first k minus 1 terms. So thus, by looking at these, we get k factorial is actually k times k minus 1 factorial. So therefore, you can, so among these two terms, okay, circled terms, you can take out k minus 1 factorial as common factor. So that's why we get here. So this part give you the extra k. Now the other part give you a factor 1, so you don't write it. Okay, so you take out k minus 1 factorial, you get the first factor give you k, the second factor give you 1. Now I want to do the same for, actually I want to do the same for, where is a clean, okay, so here. So n minus k plus 1 factorial is 1 times 2 all the way to n minus k, but n minus k plus 1. Right, that's the largest number. Now if you look at n minus k factorial, so this is 1 times 2 all the way to n minus k. So therefore, if you compare these two, you have a common factor of, now I change the color of the pen, n minus k factorial, right? Now, for the first fraction, downstairs, it only have a copy of 1. For the second, n minus k plus 1 factorial, you have this extra term, n minus k plus 1. So you get something here, right? So this is the result after we take the common factors from the denominator, right? So we get this. And then then it's just calculation. So you you simplify the term in the square bracket, you get this, right? Now, putting these things back, right? K combined with k minus 1 factorial, you get k factorial. This term, n minus k plus 1, combined with n minus k factorial, you get this bracket n plus 1 minus k factorial. On top, again, you can combine. So this is a product from 1 to n. Now you have n plus 1, so you get n plus 1 factorial. So you get a funny term like this. But this is exactly n plus 1 choose k. Okay. Now if you do this, you don't need to think. You just manipulate symbols. If you do the counting argument, and then you have to think a bit, right? So both proof, I think, has some interesting features. Anyway, so in any case, we justified this equality of the two combinatoric numbers. Okay, is that all right? Okay, now let's apply the binomial theorem to determine the size of power set. Okay, so remember that if X is a set, the power set curly P of X is the set consists of all subsets of X. Right? We have seen it several times, especially in the Cantor theorem. We know that even for infinite set, the power set is larger and so on and so forth. Okay. Now, for finite set, suppose the set capital X has n elements. The question for you is, how big is the size of the power set? It is still a finite number, right? So how big is it? Now, we can calculate the size of power set systematically. Like we actually see examples, right? So you see for each k between 0 and n, the number of subsets of X of size k is n choose k. Okay. So therefore, you count the number of subsets of X you just count the number of subsets of X of size 0, and then size 1, and size 2, all the way to size n, right? So you add them together, this will give you the total number, give you the size of power set, right? So the power set of X is the sum of these binomial coefficients. Now, do we know how to calculate this? Okay, so the trick is to put A equal B equal 1 in the binomial theorem. Okay, so let's see. Where is the binomial theorem? If you put A equal B equal 1, right, the right-hand side is the sum we want. It's from n choose 0 to plus n choose 1 plus dot 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 plus n choose n. But the left-hand side becomes 2 to the n, because this is 1 plus 1 to the n, right? So inside binomial theorem, if you plug in A equal B equal 1, you get 2 to the n equal the sum of these binomial coefficients. So fast forward to here. This 2 to the n is the sum of these binomial coefficients. Okay. So, so that shows the size of power set is the power, is 2 to the n. So in some sense, it justifies why do we call it power set? Because the size is 2 to the power of n. Okay, so now let's move on to the last batch of examples of counting. So they are all variations of the same theme. So we want to count. Okay, so the scenario was this: you have a grid, you have a map, so it looks like a grid. Now, you want to go from point A to point B, right? If you go up, you call it north. If you go to right, it's east, right? So the B is at the northeast corner. So now, okay, if you are allowed to go either up or to the right, and you do not allow, you are not allowed to backtrack. You can only go either up or to the right, right? Now the question for you is, how many ways can you go from A to B in this grid? Okay. So this is a counting problem, but we don't have a formula to plug in yet. So we have to analyze the problem a little bit and turn it into a form that we understand. Okay, so the solution is this. So let's consider a possible route, right, going from A to B. So for example, this red segments, zigzag segments, right? So we want to convert this path, so suppose you have this red path, into a string of integers consisting of zeros and ones. Okay, so whenever you move to the right, to the east, you code it or you label it 0. Whenever you go up, you label it 1. Okay, so this particular path corresponding to 0, 1, 0, 0, 1, 0, 1, 0, 0. Right? So each of these paths is corresponding to a binary string. Okay. Okay, so here, so the binary string corresponding to the path, okay, I don't want to read this. Okay, so it's like this. The total length of the string will be 9, right? Because the grid, the dimensional grid is, so you can only go, you need to go 6 steps to the east, 3 steps go to the north. You can't skip any of these steps. So the total number of steps is definitely 9. Okay. So now among the 9, so among the okay, so the length of this 0, 1 string, the binary string, is always 9. which is the sum of the dimension of the grid, right? Because as I said, you have to go 6 steps to the right, 3 steps up anyway, right? So its total step is 9. Now, for this grid, because it's 6 times, you have 6 zeros, because you have the horizontal distance was 6, so therefore you have 6 zeros and 3 ones. That's the vertical distance. So in other words, so this is clear, right? So corresponding 0-1 string always have 6 zeros and 3 ones, because you are not allowed backtrack, and so you have to go 6 steps to the right, no matter how interlaced with the vertical step. You have to work to the east 6 steps, right? Okay, so on the other hand, if I give you a binary string or 0-1 string of length 9 with 6 0 and 3 1s, it always gives you a path from A to B, right? So I'm trying to say counting the possible root is the same as counting possible strings, the number of strings. So I'm changing the counting problem from this geometric, from these, into counting the number of strings. Okay. So by the analysis above, the required number of different roots is equal to the number of different 0-1 strings of length 9 with 6 zeros and 3 1s. Right? So we change the counting problem into an equivalent counting problem. Now the new counting problem is easier, right? So it's like choosing, so for example, it's like choosing 6 zeros, 6 positions out of 9, right? So this is like choosing 6 different places from 9 different places, right? So the place I choose are the ones I'm going to put a 0, okay? Or you can, because if you fix the 6th position, the other 3 positions automatically go to 1, so you have no choice, right? So therefore, the counting the number of strings is like counting. You choose from 9 positions. You choose 6 different places out of 9. Okay. Equivalently, it's like you choose 3 different places from out of 9. The 3 different places are those you are going to put a 1. Okay, so the number will be the same. So, in short, the total number, the number required, is given by 9 choose 6, right? Which is the same as 9 choose 3. So it is this number. So I didn't simplify. You can simplify it. Okay, so so this example serves as a typical example of counting different roots from the regular rectangular grid. You are going to see other problems in homework and tutorial. Okay, so now let's look at a variation. So once we know the basic technique to count the number of roots, we can look at some variations. So here's a typical variation. So how many possible bus routes moving, either east or north, is just like the grid thing, are there from 0, 0 to 8, 8 that pass through 3, 3 or 5, 5. Okay. So, so the picture would be, so here is 0, 0. Here is 8, 8, right? I will not draw the whole grid. But somewhere here you have 3, 3. You have to pass through. Somewhere here you have 5, 5. Right? So now you count the number of ways, you first go here, you go there, and then somehow go there, right? So the problem is, okay, so you want to go from 0, 0 to 8, 8, but the condition is when you work, you have to go through these 2 points, one of these points. So you go through 3, 3, or you go through 5, 5. Sorry, maybe the picture was misleading. So you can go to here, and then maybe you go somewhere, or you can go somewhere here. Hey, this is bad. You can. Where's the eraser? Anyway, so you don't need to go through three, the 2 middle points. As long as you go through one of them, it's fine. Okay, so now let's look at solution. So let A denote the set of roots from 0, 0 to 8, 8 that pass through the first point, 3, 3. Let B denote the possible roots which pass the second point, 5, 5. Now we want to compute, because this is a OR, we want to compute the size of the union, right? Okay. So we know the method to count the size of union is this PIE, the inclusion-exclusion principle. So therefore, we carry out the plan. So how many elements are there in A? So what is A? Now let me draw a more accurate picture. So what is A? So here I redraw the grid 0, 0 to 8, 8. Now for set A, I only consider one point, which is 3, 3. So the possible route I'm looking at is I first go to A. I first go to 3, 3, and then I continue my journey to 8, 8, right? So I have to pass here. Okay, so we can use multiplication principle. So to count the number of elements in A is like I accomplish the task in 2 steps. The first step is I go from 0, 0 to 3, 3, and the second step is from 3, 3 to 8, 8, right? So I just need to count them separately and then multiply them. Okay, so the answer is okay. Okay, now you know by the basic example, from 0, 0 to 3, 3 is like 6 choose 3. Because right, you see, you have to go 3 steps to the right, 3 steps up. So total number of steps is 6. Among the 6, you have to choose 3. Right? So this is the number of ways you go from 0, 0 to 3, 3. Now similarly, from 3, 3 to 8, 8, you have this number, okay, by the same reason. So it gives you this 5040. Now similarly, B, you count how many ways. First go to 5, 5, and then from 5, 5 to 8, 8. So you get this number. It turns out to be the same. Okay, now what is A intersect B? A intersect B is, if you travel, you have to pass through both. You have to pass through 3, 3 and pass through 5, 5. So you count the possibility, you think of your task has 3 steps. First go to 3, 3, then 3, 3 to 5, 5, and from 5, 5 to 8, 8, right? So for each of the step, you have, okay, these many ways, okay? So for example, in the middle step, right, you go from 3, 3 to 5, 5. So here, this guy is go from 3, 3 to 5, 5. So you go 2 steps to the right, 2 steps up. So it's like totally you go 4 steps, but you have 2 of them are zeros, or 2 of them are to the right. So the total number is 4 choose 2. Okay. So the total number of elements in the intersection is this. Okay. If you multiply, you get that. Now by the PIE, you know the size of the union is the sum of size of A plus size of B take over intersection. So it's just this. So you'll see more examples in your tutorial problems. Okay, so that is the lecture 7. I should have finished it last time. Right? Okay. Now I think it's still early, so let me continue a little bit of the new lecture, and then we stop at the natural place to have a break. Okay, so now I want to change topic. So the new topic is probability. Okay. So so we are going to have 2 lectures on very, very basic probability. So probably again, lots of you probably know it from JC, but we don't rush. We just do things in a slow way. Okay. So the outline is, first I give you some motivation, right? So to link from counting to probability. As you know that these 2 things are related very much, okay? And I'll give you some examples. And after that, actually, there are some terminologies. Actually, it's, again, if this is the first time you see it, it is quite heavy, right? But anyway, we'll see how it goes. Okay. So we'll introduce several terms here. Okay, so let's look at the easy part. So in the end, I'm going to answer 2 questions. So I'll give you two scenarios. I call it motivating examples. So the first example is, okay, let's call it birthday problem. Okay, suppose someone offer you the following bet, right? So he claims that there are 2 persons in this LT right now with the same birthday. Okay, and then he offer you some money, right? So the question is whether you are going to accept the bet, whether you are going to bet with him. Okay, so you'll see that probability theory will help us. Okay, so what is probability theory? So the goal of probability theory is to model uncertain situations or uncertainties and quantify the uncertainties involved. Okay, so for example, you don't know, right? You don't know whether people in this hall have same birthday, so you have to take chance. So there are certain uncertainty, right? The probability will help you, right? So you do some calculation, and then it helps you to make decision. Okay, so this problem probably doesn't make sense, especially in this situation. Right? We have so few students. Last year when I taught the last year the things are not too much better, but obviously it's more. So there are about more than 30 students. So I did pass a piece of paper, ask them to write the birthday, and it turns out they are people who, among I think the attendance was maybe 30 to 40 students, and then indeed there are two person has same birthday. Okay, I think now the sample size was too small. I don't want to pass the paper. Okay, I'll pass you a piece of paper for different purposes, but not for birthday. Okay. Now the other example is more interesting, and now with the help of internet, if you have a nice example, nice problem, then it becomes well known. So most likely you have seen this before. So, but it's interesting. Okay. So let me go through this. Pretend you haven't seen it. Okay. Suppose there's a let's call it popular quiz, right, in a party. So this is also called Monty Hall game, whatever. So the game, the problem is like this. Okay. So there are three doors. So there are three doors, and you are asked to guess the door behind which is the ground. Okay, so there's a car and two garbage, goat or whatever. So you are asked to guess behind which door there's a car, there's a prize. Now after you pick the door, the host, okay, so the person who is the host of the game show, okay, he knows where the car is, right? Now you choose a door, okay. So the host open one door, one of the other door to reveal a goat, right? Because there are still two doors left. At least one of them there must be a goat somewhere. So he will open one. Right? Okay. So he will open one, show you, oh, there's a goat, and ask you if you want to change your choice. Let me try again. So in the very beginning, all the doors are closed. Okay, you don't know what, so you're asked to pick one. So you pick one. You pick, I don't know, maybe the first one. Imagine these are all closed, right? And then the host will open one to show you a goat and ask you, do you want to change your bet? Change your choice. Okay, so that's the question. So you would think, why should I change? Because everything was random, right? I just pick one, and then if I change, what difference does it make? It seems that it's irrelevant, right? Now we are going to see whether you should make the change. You can think of it if you haven't heard of this problem. Okay, I hope I'm clear about the question. Right, three doors. You point one, then host open one with a goat. Ask you whether you want to change. Okay, so then we are off. We talk about probability, and then in the end we come back to answer the two questions. Okay, the birthday question and the Monty Hall show. Okay, so first I want to go from counting to probability. Okay, so recall that in the game of poker, we have calculated all possible five cards hand, right? So the total number is 52 choose 5, and this is like 2 million whatever. Okay. So the total number here is an example of something we will call sample space, and the particular way. Okay, so we look at some subsets of these hands, right? They have special names called royal flush, or so the total number, the number of ways is 4, and so the chance you get this royal flush is 4 out of the total number. So it's 4 divided by this is extremely small probability. Okay, so the number is extremely small. Now there are other subsets, right? There's a collection of 4 of a kind. We calculate last time the total number is 624. So if you calculate chance, is you use 624 divided by this number, so you get this percent, 0.0240%. Okay. So obviously that you have higher chance to get 4 of a kind. Right. So that's why the casino rank the different hands, the reward for different hands in different ways. Right. So that explains why they are ranked in certain way. Okay, so now we want to introduce some names which are quite natural. Just follow your. Okay. So in this lecture, I'll call an experiment is a situation whose result or outcomes depend on chance. Just call it the experiment. I'll call it an experiment. Okay. So for example, tossing a coin is like an experiment. Okay. So the result depends on chance, right? So there are two possible results, two possible outcomes, whether it's a head or a tail. Okay. Or you are throwing a dice. Here, I don't know whether I'm grammatically correct, or some people just write die, or but sometimes people also use dice for a singular form. So don't be too picky on me. So you just throw something. Okay. So there are 6 possible outcomes, right? So it's like a small square. On each side there's a number written on it. So a square, the cube has 6 sides. So you have 1 up to 6, right? So there are 6 possible outcomes. So I'll call it experiment. Throw a dice is an experiment. Or picking a card from a deck. So again, I'll call it an experiment. So there are 52 possibilities. Or I can toss a coin twice. Right? So now there are 4 possible outcomes. Right? Okay. So these things are examples of experiment. Okay. Now, the set of all possible outcomes of an experiment is called the sample space associated with this experiment. Okay, so an element of the sample space is an outcome of the experiment. So, for example, suppose the experiment is tossing a coin, the sample space consists of 2 elements, right? So because there are possible outcomes, right? So the elements are called head or tail. Okay? So each element here is called an outcome of the experiment. This is just common sense. Now, in the example of throwing a dice, so the sample space has 6 elements, right? Now, the picking a card, it has 52 elements. Tossing a coin twice, you get the sample space is of size 4 because it's head, 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 tail, tail, head, tail, tail. Right? Okay, so an event associated with an experiment is a subset of the sample space of the experiment. Right? So now you have sample space. Any subset is called an event. Okay. Now, for example, look at this experiment, throwing a coin twice, right? So the sample space we saw is this 4-element set. Now, what is an event? What is an example of event? So the event, this is an example, getting the same result twice. Right? So you get head, head, or tail, tail. So this is a subset of the sample space. So this is called an event. Right? So now, so the event, you can write it mathematically as a subset, right? So this A is head, head, tail, tail. Okay. Now you can do this for another experiment, right? So in the experiment of throwing a dice twice, for example. So the sample space become 36, right? Because the result of first throw, there are 6 possibilities. And then the result of second throw is another 6. So total combination is 36, 6 times 6, right? So the sample space of this size. Now the event of getting the same number means you get 1, 1, or 2, 2, or 3, 3. So it's given by this subset, right? 1, 1, 2, 2, 3, 3, and so on and so forth. Right? So this is called the event. Actually, any subset is called event. Now, some events are called equally likely. Right? If each outcome of an experiment has as much chance of occurring as any other, then we call them equally likely. It's just use common sense. So this is kind of fairness. So there is no preference of any particular outcome over others. So it's like throwing a unbiased coin, right? So it's equally likely you see head or you see tail. Okay, so here, so tossing a fire coin, so a head or a tail is equally likely, right? So now we want to introduce the mathematical way. So you say the probability of head is equal to probability of the tail, which is half, right? Or you toss a dice. So each of the 6 faces is equally likely. So we'll say the probability of getting any number on the dice is 1 out of 6. Okay, so in general, you can calculate probability in this way. So let A be an event in the sample space S. Okay, you just say A is just a subset, right? So the probability of event A, denoted by P of A, is the ratio of the size of A divided by the size of the sample space. And that's the probability. Immediately you see that computing the probability actually is more or less counting. Right? You count how many numbers in A and how many numbers in S. We have to say that in this course we only consider finite sample spaces. If you study the real probability, you see there's continuous case, right? But this is a general education module, so we only consider the simple cases where everything was discrete and finite. So we don't consider those integrals and so on. Okay. But I hope this is fairly intuitive, right? So you have an event and you want to calculate the probability of that event. So the way to calculate is just you count the size of the event divided by the size of the sample space. Now let's look at an example. So tossing a coin 3 times, right? So the sample space are like this. So it's 2 to the power 3, right? Because the first toss has 2 possibilities, second also 2 possibilities, the third one also 2 possibilities. So the total number of combination is 2 times 2 times 2, which is 2 to the power 3. So it's 8. Right? Now, suppose the event is all 3 have the same results. So this event is HHH or TTT. Now the probability of that event is just the size of A divided by the size of sample space, which is 1/4. Okay, so now let's look at some calculation. So if you toss a coin 6 times in a row, what is the probability that you get more head than tail? Okay, try again. So you toss a coin 6 times, right? And then the event will be more head than tail. Okay, now you want to calculate the probability of that event. Okay, so let's do things, follow the definition. So the size of sample space, right? So the sample space S has size 2 to the 6, right? Because, okay, you can think of, you have 6 steps you have 6 tosses, right? So each toss has 2 possibilities. So by multiplication principle, you multiply the 6 2 together, right? 6 2s together, so you get 2 to the 6. So this is 64. So that's the size of sample space. Now, let A be the event of more head than tail. So this as a subset of S. Okay, so we want to count how many elements in A. Okay, so we split A into disjoint union of the following subsets. So more head than tail, it means one of the possible cases. So one is exactly 4 heads, right? Then there are 2 tails, so more heads than tail. The second case is we have exactly 5 heads and only 1 tail. So again, more head than tail. The last one is we have everybody was 6 heads and only 1 tail, 0 tail, right? Okay, so if you first you agree with me that A is the union of these 3, right? Because the previous case will be 3, 3. 3 heads, 3 tail. So then it's not more heads than tail. They are equal, right? So we won't consider that case. So the A indeed is the disjoint union of 1, 2, 3. Okay. Now let's count the number in each of the items. So the first one is I claim is 6 choose 4, right? Because you have 4 heads, so it depends on which position it shows up. So it's among the 6 tosses, you choose 4 positions. So it's 6 choose 4. Now, by the same reason, there are exactly 5 heads is 6 choose 5. The last one is just 1, right? No choice. So the size of A is the sum of these. So it's 20, 22. Now the probability of A is the size of A divided by the size of sample space. So that gives you this number. Okay, maybe I'll cover this and then we take a break. Okay. So you see that there's a close relation between counting and probability. Right? So calculating probability is like counting different sets. So all the principles we learn from counting, they have more or less parallel version in probability. So now let's go through some of these. Okay. So there are something called addition principle. Okay. So if A and B are disjoint subsets of S, we also say that A and B are mutually exclusive events. Well, just change the name. Right? So then the probability of A union B is PA plus PB. The reason is this, right? Because if they are disjoint, the size of A union B is just the size of A plus size of B. So therefore, by counting, you immediately derive the probability. Okay. Now for probability, you can also have this inclusion-exclusion principle. We also call it PIE, the pi. So if A and B are events, then the probability of A union B is PA plus PB minus P of A intersect. Again, this is straightforward from what we learned in the previous lecture. Also, if we use A to the power C to denote the complement of A in S, the relative complement, and then the probability of the AC, A to the power C, is 1 minus the probability of A. Right? So in other words, AC is A doesn't happen. Okay? It's a negation of A. A doesn't happen. So the probability of A doesn't happen is 1 minus probability of A happens. Right? So this is again very, very intuitive. Okay, so let's take a break, and after break we'll do some more examples. I need to have your name so that because the university requires this. Okay. So let's continue. We'll see more and more examples. Right? The examples are all very simple, but let's look at them one by one. Okay, so the question one is this. So a glass of jar contains 1 red, 3 green, 2 blue, and 4 yellow marbles. Okay. So if a single marble is chosen at random from the jar, you choose one, right? And each such marble is equally likely to be true. Sorry, I should change this to marble. So now the question is, what is the probability that is yellow or green? Okay, so the answer is we turn it into sort of like a counting. So the probability of yellow or green, we use the addition principle, right? Because yellow and green are disjoint. The marble, if you are yellow, you are not green. So they are exclusive. Right? So the probability of Y or G, yellow or green, is probability of yellow plus probability of green. Right? Now, what is the probability of yellow? You have 4 yellow marbles. The sample space is 10. If you add them, you get 10. So it's 4 over 10. Now, similarly, the probability of green is 3 over 10. So altogether, you have 7 over 10. Right? So that's a simple example. Okay, now the second one is slightly more complicated. Okay, now we draw a card. A single card is chosen at random from a standard deck of 52 cards. Right? Now the question is, what is the probability of choosing a king or a club? Okay. So again, we are counting a union, right? So probability of joint events, right? So it's either you draw a king or you draw a club. Okay, now this time there's the two events has intersection, right? So there's a card called club king, right? Okay, so the probability of king or club is equal to probability of king plus probability of club, then minus the intersection, probability of the intersection. Okay, so now let's count. So what is the probability of getting a king? So there are 4 kings, right? So it's 4 over sample space, the size of sample space, 52, plus the probability of clubs. So there are 13 clubs, so it's 13 over 52. Now in the intersection, there's only one card, which is the club king, right? So you have to minus 1 over 52. So this is your answer. Okay. Now, the same thing, same idea, one more variation. Okay, so an integer between 1 and 100 inclusive, so including 1, including 100, is chosen at random. So find the probability that it is a multiple of 2 or 3 or 5. Okay, so you draw a number from 1 up to 100. You want to find the probability of a number which is either a multiple of 2 or a multiple of 3 or multiple of 5. So let's do it. Follow the definition. The sample space is this, from 1 to 100. So the size is 100. Now let A, B, and C be the events that the chosen integer is a multiple of 2 or 3 or 5 respectively. In other words, A is the event that the chosen number is a multiple of 2. Okay, and so on and so forth. So let x sub k denote the set of integers in S which is a multiple of k. For example, x sub 2 will be the integers between 1 and 100, which is a multiple of 2. Right? X sub 5 will be the integers here, which is a multiple of 5. Okay? Okay, so now we are going to use PIE, the inclusion-exclusion principle. But this time, the intersections are more complicated. So we have to use all these informations. Okay? So let's look at these. So we can calculate x sub 2, which is the number of even numbers between 1 and 100. So it's 100 divided by 2, so it's 50, right? Now, x sub 3 is 33, right? Because the integer part of 100 over 3 is 33. And x5 is 20. So now we have to calculate the intersection. Now, luckily, these numbers, 2, 3, and 5, okay, they have no common divisor. So the counting was simple. So the common, how to say, if you are a multiple 2 and a multiple 3, actually you are multiple 6 in this particular case. So this is okay. The intersection is actually the same as x6. So it's easy to count. Now for the same reason, we are lucky, right? 2, as I said, 2, 3, and 5, they have no common divisor. If you have common divisor, it's a little bit more complicated. So in the simple case, it's straightforward to calculate the size of the intersection. Now the size of the three-way intersection, x2 intersect x3 intersect x5, in other words, the numbers which is divisible by 2, by 3, and by 5 is actually the x30, so which is 2 times 3 times 5. So it's x30 here, so the number is 3. Okay, and then it's up to you whether you want to count, use probability formula or use the counting formula. So let's use probabilities. So the probability of A is 0.5, right? Is 50 divided by 100. Is the event, the size of event divided by the size of sample space. So it's 0.5. And these are similar, so I will not read. Okay, so then by this PIE, you have to add PA plus PB plus PC, take away the two-way intersection, take away these, then plus the three-way intersection. So in the end, you get this. So it's quite big, right? So the probability is 0.74. So now we can look at the so-called motivating examples, right? So let's see the birthday problem. Okay, so so let me remind you the problem, right? In a group of n people, now here n equal 9, including me 10. Okay, 10 people. So what is the probability that there are 2 persons with the same birthday? Okay, so first, this is a very common trick. Sometimes it's hard to compute an event, the probability of event, but it's easier to count the probability that the event doesn't happen. It's easier to count the complement. Okay, so this is a case. Okay, so I want to count the probability of 2 persons with the same birthday in this way. I'll use 1, then subtract the probability that this thing doesn't happen, right? If it doesn't happen, means the n person all have different birthdays, right? Because no 2 person has the same birthday, so they all have different birthdays. Okay, so what is the size of sampling space? So we have n people, so each person have okay, let's assume there's no leap year, right? 365 possibilities. So the sampling space is this number, the number of days to the power of n. So that's the sampling size. Now let A be the subset of S where the n persons have different birthdays. Okay, so this is a subset of S where the n person, they all have different birthdays. Okay, so now what is the size of A? Okay, so let's calculate. So the first person, maybe me, so I choose my birthday. So is one of the possibilities, right? Now, after I choose my birthday, you cannot choose the same birthday because we assume we all have different birthdays. So you have one less choice, right? And so on and so forth. So now we have n persons, so the product has n factors. So from 365 all the way to 365 minus this n minus 1. Okay. So this is, you can write it using factorial. So this is 365 factorial divided by the 365 minus n factorial. So that's the size of A. Okay. So therefore, the probability that two persons have the same birthday is the complement of the thing, right? So this is 1 minus the probability of A, which is this number divided by. So let me add this. So probability of A will be A divided by S, right? So is this number divided by 365 to the power of n, right? So the circle number move up there, right? So this is a circle number divided by this number. Okay. So the probability of two persons have the same birthday is calculated by this formula. So now let's plug in n. Okay, so the critical point is n equal 23. If you plug in 23, you get more than half chance. You get 50.73. Now in this, now we have 10 persons, so the probability of getting two persons having same birthday is just 11.69. So it's like 1/10. So it's not very big chance. Okay. Now, right. So I told you that 1 year ago we have between 30 to 40 attendants. So indeed we see there are two persons have same birthday. Okay. Actually, if we have 30 people, the chance was quite high. It's 70%. Right? If I have 50 people, then it's almost surely we'll have some people have same birthday. Right? So this is I don't know. It's a little bit surprising. Right? You wouldn't think that, suppose we only have 30 people, that the probability is so high, but by calculation it is. Okay. Anyway, so that's the answer of the first problem. I don't know whether I can. Then after that, there's lots of other stuff. Maybe I don't have time to talk about this. The second example, the changing, whether you switch the door. Okay. Anyway, so let's go through the items slowly. So now I'm going to introduce quite a number of terms in probability theory, but they are all very simple terms. Okay, so the first thing I want to introduce is independent events. Okay. So suppose you toss a fire coin twice, right? Would you expect the outcome of the first toss to influence the outcome of the second toss? The answer is probably no, right? Because after you finish the first toss, it has nothing to do with what will happen for the second toss, right? So intuitively, the answer should be no. But this leads to a very general and important concept called independence. So in other words, think of this as two events, right? Are these two events related, or they have no relation at all? I mean, either they are related, they are dependent or independent. Okay, so independent is a mathematical way of describing that the two events has no relation. They don't influence each other. Okay, so the mathematical definition is goes like this. So let A and B be two events. We say that A and B are independent if now we don't explain the meaning. We just look at the code numbers. We just calculate. We calculate the probability of A intersect B, and we calculate the product of PA and PB. If they are equal, we'll say they are independent. If they are not equal, we say they are dependent, right? Is this okay? So, okay, now how about we have three events, right? Mutually independent. Suppose we have AB3, they are mutually independent. It means, okay, these formulas. Okay, so A intersect B, the probability of A intersect B is PA times PB. And okay, so you can read. So this is the definition of three-way independence. Okay, this is very natural, right? The events are not independent is called dependent. Okay. Now, examples, right? So let's see. So suppose we toss a coin twice. Now we look at two events and determine whether they are dependent or independent. Okay, so let A be the event of getting a head at the first toss. We toss a coin twice. The event A is, in the first toss, we get head. Event B is the event getting a tail in the second. Okay, so the claim is A and B are independent. Intuitively, this is the case, right? Because the first toss and second toss, they don't influence each other. Let's check the mathematical definition to see whether the mathematical definition catch this. Okay, so let's try. So what is the sample space? So it's this, right? The size is 4. Okay. Now what is A? Okay, A is the event of getting a head at first toss. So A is this, HH and HT. The first two items belong to event A. Now the B is the second two items, right? So the second, the B is getting a tail at second toss. So it's HT and TT, right? So these are B. So the intersection, there's an intersection which is HT. Right? First time you get head, second time you get tail. Now let's calculate the numbers. So probability of A is half, probability B is half, probability of A intersect B is a quarter. So now since it fits the formula, PA times PB is a P of A intersect B, A and B are independent. Okay, so that confirms our definition is reasonable. Right? Okay, so now let's look at another example. Almost the same. Okay, so a fair coin is tossed twice. Now we have C and D defined this way. So let C be an event of getting at least one head. Right? So it could be first time head or second time head or both head. Right? Then D be the event of getting at least one tail. Okay. Now the question is, are C and D independent? Okay. So, well, probably this time it's very hard to judge whether they are related or not. It's better to use just calculation, right? Mathematical formula. Okay, again, sample space is this. Now, C, as I said, you could have the first time head, you could have second time head, or you have both time head. So C is the set of these three elements. So the probability of C is 3/4. Similarly, D is, okay, the probability of D is 3/4. Now, what is the intersection? So intersection will be at least one head and at least one tail. So it's a HT or TH. So the intersection is this set, right? And the probability of intersection is half. Now, if you calculate the product of PC times PD, is not equal to the probability of P of C intersect D. So they are not independent. In other words, they are dependent. Okay. Okay, so there. Okay, I don't know why so many examples. Okay, so let's try this. Okay, now a loaded coin. The loaded coin means a biased coin. So a fair coin is if you toss, there's equally likely chance to have head and tail. A loaded coin means maybe there's more chance to have head, or so it's biased. Okay, so a loaded coin is tossed 5 times. So assume that the probability of a head is 0.6, right? So there's more chance to get head, okay? And that the tosses are independent of one another, right? So now find the probability of obtaining these A, B, C, D. So A says O tail, B says at least one head, C says exactly one head, D says exactly 2 heads. Right? You want to calculate the probability of these events. Okay, so let's go through them one by one. So the probability of tail is 1 minus. Suppose I just toss once, right? The probability of getting a tail is 1 minus the probability of getting a head. So this is 0.4. Okay, so now look at A. So the probability of getting O tails is the probability of, okay, I describe the events as this, T, 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 T. They're O tails, right? So it is because the events are independent. So this is PT times PT times PT. Okay. So this is 0.4 to the power of 5, so this is a probability. Now, how about the events, the B? B says at least one head, right? Sorry. So the B says we want to calculate the probability of at least one head. Okay. So here, again, we use we go to the complement. So the complement is no head, right? So therefore, the probability of get at least one head is 1 minus the probability of O tails. So we calculate the probability of O tail, so we get this. Okay. Now, the third part C says we want to calculate the probability of exactly one head. Okay. So exactly one head, we have 5 tosses. So okay, these are the 5 possibilities. Okay. Now if you add, if you calculate, so you have 5 times, 5 means the sum of 5, but the probability are all the same. So 5 times. The head, to get a head, you have 0.6 chance, right? To get a head, the remaining 4 tails is, each of these is with probability 0.4. So 4 of them will be 0.4 to the power of 4. So altogether, the probability of each item is 0.6 times 0.4 to the power of 4. So altogether is 5 times this, so you get that. Now, how about exactly 2 heads? So again, you have to, suppose we do this using slow motion, right? So you have to list all the possibilities. So among the 5 tosses, you have 2 H, right? So altogether is 5 choose 2, because the H can appear at different combinations. So it's 5 choose 2 of them. Now, each of the item happens with probability 0.6 squared, which means the 2 heads, right? And then followed by 0.4 to the power 3, because these are the probability of having tails 3 times, right? So altogether is this, so you get that. Okay, so more terms. So now we want to introduce something called binomial distribution. Probably you learned this in JC, I think. But anyway, so let's look at an example. So suppose that a coin is tossed n times, and the probability of a head in each toss, okay, getting a probability of head in each toss is p. Just like those loaded coin, the early example, the probability of getting head is 0.6, right? So now the p is the 0.6. Okay. So now, assuming that the tosses are independent, and then the probability of exactly k heads, there's a formula, right? You see in the early example, you already see the pattern, right? So we calculate the probability of one head, exactly one head, the probability of exactly two heads. Then you may ask yourself, what happened to the probability of exactly 3 or 4? So here, in general, we can calculate in this way. So suppose we have n tosses, and then the probability of head is p, right? So now, what is the probability of exactly k heads? So we write it as p bracket x equal k. I will say the notation. I'll say more about notation in a minute. Okay. So we use p of bracket x equal k to denote exactly k heads. So the calculation is done in this way. So first you locate where are the k heads appear. So there are n choose k possibilities, right? Just like among the 5, you have 2 heads. So this is n choose k. Now in each of the item, you have exactly k heads. So the probability is p to the power of k, right? Then followed by the rest are the tail. So the probability is 1 minus p to the power n minus k, right? So so here the sample space has size 2 to the n. Then there are this many elements in S with exactly k heads, so the probability is this. So this kind of X will have a fancy name for them. We'll call them random variable. So a random variable is so in this particular example, is it takes the value of the number of heads. So in general, I don't know. I leave the later we'll see the random variable a couple more times, but I will not define what exactly means for random variable. I'll leave it to the probability class. So anyway, so this is about binomial distribution. Now let's look at another example. So the title of this slide was misleading. So it's not a monkey. Okay, so the example mentioned monkey, but these are not example of monkeys. So the scenario is this. Assume you have a monkey types at random on a typewriter. So, or it jumps on the computer or whatever. Okay. So then it produces a sequence of some garbage, right? Like 1 million alphabetical letters without space. So he jump around or he types. And now we divide the sequence into blocks of 6 letters. So you have 1 million, a string of 1 million letters. Now you chop them by 6, right? 6, 6, 6. Okay. So assume that the letters are produced independently, because that's the purpose of monkey, right? So he doesn't think, he just punch. Okay. So these are independent. So you don't know what he's going to type. So assuming that letters are produced independently of one another, and each letter is equally probable to be typed out. Okay. Now we want to find the probability that one of these blocks is the sequence genius. Okay. Right. So the monkey types 1 million letters. You want to find out what is the chance of his typing with the word genius. But we only count in a fixed way. We cut 6 letters. We don't shift. We don't consider what happens, say, like 4, 5, 6, 7, 8, 9, genius appear there. We don't consider the case. We just chop into pieces and look at each piece. Okay, right. So this is the problem. Okay, so now let's look at the solution. First, there are these many blocks, right? So you have 1 million, a string of 1 million long. You chop every 6 digits. So this is the number of blocks, number of words you get. Okay. So the probability of a block is this genius, is the thing we want, is okay. Each letter is random, right? It's 1 over 26, assuming the keyboard only have 26. And you have 6. The word has 6 letters, so the probability is 1 over 26 to the power 6. Okay, so that's the probability of the word. Now the probability that none of these letters is a genius is 1 minus p to this power. Okay, so let's first forget about the rest, right? So let's see. Suppose none of these are genius. So the first one is not, the second one is not, and so on and so forth, right? So the first one is not, is 1 minus p, right? The second one is also not. So it's a so you multiply, right? So you multiply 1 minus p this many times. Sorry. Okay, let me repeat one more time. So the probability, let's look at second line first. Right? So the probability to get the result is p. To get the genius is p. So therefore, the probability to get garbage, which is not genius, is 1 minus p. Okay. So now let's assume none of these words, these blocks, so they are all garbage, right? What is the chance? So it's 1 minus p times 1 minus p times 1 minus p that many times. So it's this number. Okay. So now here, okay, I want to change. So here some calculation. Okay. It's probably too difficult to calculate this power. But we have to use a trick, a mathematical trick. So the trick was, okay, so first I multiply some number, divide by the same number. So this is the same as p. I just add a fraction 1. Okay. So why do I add this funny fraction? Because I want to use this formula. So in mathematics, we can approximate this. Okay. So there is a mathematical fact. There's a mathematical fact. So for any x, 1 plus x bracket 1 plus x over n bracket n is more or less e to the x, where e is the base of the log. E is the Euler constant we learned in first week. Okay, so e is 2.7 something. Okay. So we want to use this mathematical fact, which says for any number x, the one, okay, this funny thing is roughly e to the x. Okay, so now think of this as n. This n, this is n. Now this x is minus 16666p. Okay, so this looks like 1 plus x over n to the power of n. So we multiply this number and divide by this number because we want to have these two things are the same. We want to have the exponent and the denominator the same. So that's why we multiply this this number and divide by this number. So we have this. Okay, so in this fraction, think of n as 1, okay, this number, x as minus this times p. Okay? Now, by the mathematical fact, this is in the form of left-hand side here. By mathematical fact, it is more or less e to the power of x. So in other words, by this fact is more or less e to the x. X is now minus this number, right? So by using that fact, we get this is roughly e to the this. Okay, then it's still probably tedious to compute, right? But it's probably better than compute this to this power. Okay. So you can use your computer, use your I don't know calculator to calculate. It turns out to be this almost like 1, right? So, but this is the probability of getting garbage. Right? So now the probability of getting the right thing will be 1 minus the big number. So we get very, very small chance of getting the result we want to get. So in other words, the monkey, even he typed 1 million words, if you expect him to get some result, it's of very low probability. Okay. I guess I'll stop here for today. I think it's time because I don't want so these things are new concept, and I guess I'll start from here next time, assuming you are showing up. So if you show up, I'll be here, and we'll do business as usual. Okay. So I'll stop here, and hopefully see you next time. Okay. Oh, by the way, don't forget to sign the piece of paper.